All right, the last thing that we're going to look at is regression models. Now, regression models just means that, well, I start with data and then I try to build my model from there. All right, so your goal here is to create the best model you have given data. Um, this is when, for instance, you don't have a nice geometric formula or a nice physics formula or a nice what would I say, interest calculation formula that you can go look up. And it's not a nice thing where, you can logically create it yourself. Okay, this is when you're given some raw data and you have to sort of fit the best model you can for that data. Now, it's not off, very rarely are these types of models going to be perfect. Okay? So, most of the time, your goal is to come up with the best model that you can. And we're going to skip some of the in-depth statistics and the in-depth stuff that you would go into in a really high-level math course. And we're just going to say it takes some computing power. If you have a TI-83 or a TI-84, there's a lot of regression built in to the statistics portion of those calculators. But that's not a requirement for this class. There's other types of software that you can look at, that you can buy. Again, you don't have to do that for this class, but things like SPSS and Minitab are statistical packages that do regression quite well. All right. So here's the thing. A lot of times in statistics, you look at something called correlation. All right. Correlation is sort of how well, typically the Pearson correlation coefficient is how well does a linear model fit. Okay. Now, we're not going to look at all these Pearson correlation coefficients. We're just going to look at a symbol that your calculator can give us. It's r squared. So this isn't actually a perfect explanation of what correlation is, but every single model that we get comes with either an r or an r squared. Typically, if it's a linear model, then you do a lowercase r, and it's called the Pearson correlation coefficient. All other models on your calculator give you this r squared. And it's telling you how well things fit. Okay? And if you look at r squared, basically it's always going to fall somewhere between 0 and 1. And for the sake of this class, what we're going to do is we're going to say, well, you kind of have to say 0 is the worst possible fit you can make. 1 is the perfect fit. If it's an r squared of 1, that means your model hits the data at every single point perfectly. Okay? Most of the time it's not going to do that. Most of the time we'll be satisfied if it kind of gets close to 1. And we'll be dissatisfied if it gets close to 0. Now, we have to draw sort of the cutoff line of where we want to be. And it turns out you don't want to do 0.5. So for this class, we're just going to say 0.6. If it's 0.6 or above, then we're going to say it's a fairly good fit. If it's 0.6 or below, we're going to say it's a fairly bad fit. So if it's 0.6 or above, we'll say it's a good fit. Let me write that down, good fit. And it's a bad fit. Our model's a bad fit if it's 0.6 and below. It'll never be 0.6 exactly, so you don't have to worry about the exact, but that's our cutoff point. Now, other books may give you different cutoff values. That there may be other instructors who say, oh, you have to do a 0.8 or you have to do a 0.7, but we'll stick with 0.6 for right now. All right, so here's what you're going to do. You're going to be given raw data, and we're going to have two variables. Now, one of these variables we're going to call our x variable. In this case, let's call our Brady points x, and violent crimes we'll call y. All right? And we're going to have data from some sample that gives us x values and y values. All right? Now, notice these are paired data. So this is kind of like North Dakota is kind of like the 0.4, or it is exactly the 0.478 on our Cartesian coordinate plane, meaning the xy axis. And so what our job is going to be is to take each one of these points and plot it on the xy axis, and then see what type of model this is. Okay? Whether this is linear, whether this is quadratic, whether this is exponential, whether this is a rational model. All right? And that's how we're going to start this. So let me, for the sake of time and also what's going on here, let me plot these points excuse me, on the sort of xy axis. All right, so I'm going to do something that hopefully you guys are comfortable with. When you do this, I'll start at 0 on the x, and it goes up to 28, so let's go make that a 30 on the top. We'll go halfway in between, say that's 15, and then 5, 10 in there, 20, 25 in there, 5, 10, 20, 25. Here we start at 78 and go up to 621. So let's do jumps of size, let's say 100. 100. Maybe I did that wrong. 200. Might be running out of room here. 300. 400. It's not perfect. I'll squeeze this in. All right, like I said, I didn't do that perfectly, but you get the picture, all right? So I'm jumping by 100 because that's fairly well done. So anyways, if we start with a 478, that gets us to a point right here. Okay, now by the way, it kind of looks like there's a point at 0. I'm not saying that. I'm saying that's just the 0, 0. If I do 6, 177, you get a point somewhere in there. If you do 18, 291, you get a point here. 20, 540, a point here. 28, 621, you get a point, maybe here. Now notice this does not fit exactly to anything, but does this look more like a line, a quadratic, an exponential, or some rational function? I would tend to say this looks linear. All right, we're kind of going up in this direction, so this kind of looks linear. Again, those points don't fall perfectly, but it does look linear. So if you were actually doing this, if you had the software, you would say to use linear regression. All right, so you'd go into your, the stats, and you'd plug in your 4, 6, 18, 22, and 28 into your x values, and then you'd plug in your y values as, what you see there. And you'd have your calculator or your computer, whatever you're using there, actually go and you tell it to do linear regression. Now, I'm doing this on my calculator as I'm speaking, and what happens is, whatever is going to happen, you're going to get back a regression, in this case, line, because I told it to do linear regression. Okay? So here's what I got back as the linear regression. Technically, this is a lowercase r because we're talking about Pearson, we're talking about linear. But I got back a lowercase r squared of point, let me write that in black here, 0.9250, roughly. It goes on for a long time. And I got a function that looked like y is equal to 21.65 times x plus 3.59. All right. So that line is really predicting what's happening with, in this case, the Brady scorecard points was my x. By the way, for those of you who don't know, as the points got higher, that means stricter gun laws. And so you see kind of there's this pattern where I'm not saying one causes the other, but in this sample, as gun laws got higher, the violent crime rate went up. Okay. By the way, this is only a sample of 5. If you are 5 or 6, I forget. If you look at the entire state data, there's actually not any correlation. It's not very correlated at all. Your R squared is not very good. But anyways, this line is predicting the violent crime rate based on Brady's scorecard points. So X is the scorecard points, Y is the violent crime rate. And this, by the way, is a good fit. This line fits the data that we've been given very well. All right? That 0.9250, that is a good fit. That's over 0.6, so we're good to go. And then if you get a line, you have your calculator sort of do the grunt work of it. Then you can ask questions like we did before. For instance, where would the violent crime rate be if the Brady points were 10? Where would the violent crime rate be if the Brady points were 20? So why don't you push pause and use the function that we got to predict these things. All right, so hopefully you've done that and got the following things. We want to find violent crime rate, that's Y, when 21.65 times 10 plus 3.59. Okay. I got 220.09 as the violent crime rate. And that's, I forget what units that is. That might be violent crimes per 100,000 people or something like this. Okay? And then it says, what would the violent crime rate be if the Brady scorecard points were 20? So you say your increase strictness of the gun laws, and this line would say, let me calculate it, plug that in. I got 436.59 for my answer in that case, right? So you can see sort of the power here that we're given data, and even though that our data doesn't fit exactly, what we can do is we can, still make predictions with it. Now we know these predictions aren't going to be perfect typically, but we do see sort of the types of things that are happening. All right, so don't be surprised if one state has Brady scorecard points of 20 and it doesn't come out to 436. It may come out to different than that, but it'll be fairly close maybe. If this line was a good predictor, then it would be fairly close. All right, so here's what I want you to do. I want you to look at this data, draw what's happening here, and then decide what type of model it is. All right, and this is the number of McDonald's restaurants per million people and the percentage of people who said they were happy with life. So we're going to look at this data. Again, push pause and figure out what type of model this is, and then we'll talk about it after. All right, so hopefully you've gotten sort of what's happening here. This is a quadratic looking model. And let me just do some plots. Now, don't be afraid to, when you're listing this, you don't always have to start out. So this is X and Y again. You don't always have to start out at 0 when you're doing these types of plots. Notice that, everything in the McDonald's per million, that starts out at 2.19 is the smallest, so you can start at 2. Obviously, you want to get out to 6. All right, so let's jump. Let's say that's 4. That's 6. Okay. 3, 5. So in other words, you don't have to start at 0. And same thing with the happiness level. Here we go from anywhere from 23 to 36. So if I went from, let's say that's top is 40. I'll start at 20. 30, 25, 35. So when you're doing your points here, right, 3.01 and 32 is going to be somewhere in here. 2.6 and 31 is going to be pretty close here. 4.49, 36 up here. Again, I didn't draw this very well. 2.19 and 23 you get here. 2.66, 31. You'll get pretty darn close to this, right? They're awfully close. 2.6, 2.66. 6.09, 29, you get this. So it kind of looks like a quadratic deal. I didn't draw it perfectly, but it kind of looks like it goes up, and then it's coming back down, right? Now notice that, again, we're not going through all of the points, but that's what it typically this looks like. Now here's the deal. You can actually on your, well, if you have the right calculator, you could come up with actually a quadratic regression model. And I'm going to give you this model. I can't write it in this blank, but here the R squared is 0.8909, which is pretty decent. And you get out a model that looks like y is equal to negative 2.70 times x squared plus 23.23 times x minus 12.97. All right. And so here, remember, x was the number of McDonald's per million people, and y was the happiness percentage. So we could ask things like, what would this curve, or where would this model predict the happiness level if there were 4.45 McDonald's per million people? So happiness level is y, x is 4.45. So go ahead and calculate that. And I know I will, so when I plugged all this stuff in, I got like 36.94 is what I got. And if I plugged it in incorrectly, which is a very possible thing, then I apologize, but that's what I got. 36.94 as my happiness percentage when there are 4.4 McDonald's per million people. All right? By the way, again, this is above 0.6, so this function is a good fit with the data that we have. All right, so it's a good fit. So here's what I want you to do now. I want you to take the years and U.S. debt in trillions of dollars and calculate what type of model is going on here based on drawing and seeing what it actually looks like. All right. And by the way, when you're doing these things, if we start out at 1980, it's often easy to, instead of starting out at 1980, think of 1980 as year 0. And then 1988 would be maybe year 8. And that often makes the calculations a little bit easier. 92 would be 12. 2000 would be, would that be 20? 2008 would be 28. And 32, or yeah, sorry, 36 would be 2016. Did I say that right? Yeah. Goodness. It's I get thrown off because I skip by 8s and a lot except for 92, which I skip by 4. So anyways, use 0, 8, 12, 20, 28, and 36 as the year, and you can use the debt in trillions of dollars as 0.9, 2.6, and so on and so forth. See what you actually get. All right, so if you look at this, first off, I should probably start by drawing my, all right, top is going to be 20. Here we're going to have 10, 5, 15, lots of them in there. So 0 and 0.9, we get something here. 88, 2.6, we get something there. 92 and 4.0, get something here. 5.6, 9.6, 18.9. It looks like that. Now I want you to notice something about this growth. It's not actually a nice line, okay? You might think we'll try to pattern a line. It's actually kind of curving up. So what we're having is this sort of a growth, which is the classic exponential growth. So this looks like exponential. And again, we can input these things into our calculators, or if you have a calculator that would do it, I should say. And I'm going to make sure that when I input these things, I input the years since 1980. So instead of inputting the year, what I'm going to do is I'm going to input 0 for that one, 8 for this one, 12 for this one, 20 for this, 28, and 36 for that one. Okay, so that way my calculation may be a little bit easier to read. Oftentimes, if you get into these really long numbers, the calculations tend to look ugly. All right. So anyways, what we're going to do is we're going to come up with a function, and just like I said before, this is an exponential regression type, so it's an exponential function that you're going to be given out. And the function that I got was y, let me do it blank here, y equals 1.19 times 1.08 to the x power. And in this case, r squared, which is, again, lowercase r, is 0.9656. So again, this is a good fit. We've had 3 examples where we've had good fits. All right. So if I said, what would this model predict debt to be in 2024? Well, if x equals 0, or let me say x equals basically years since 1980. If I wanted to predict the debt in 2024, I'd take this 1.19 times 1.08. Well, 2024, that would be, since 1980, 44 years since 1980. Okay, so take 1.19 times 1.08 to the 44th power, and you'll get 35.17. Now, by the way, this is in trillions of dollars. So if we kept on at this sort of a growth rate, then we'd get about $35.17 trillion, okay, of debt in 2024. Which is, by the way, again, that's quite a bit of debt. Quite a lot of debt. So that's kind of what your model's predicting. Now, I want to say something about the models that I've gone over so far. So far, the models that I've gone over have been a really good fit. Okay? That's not always going to happen. All right? A lot of times, like, well, for instance, these 3 models that we looked at have kind of a nice pattern. There are times where you draw this and, you know, the pattern is just all over the place. There's no pattern in general. Okay? And so that if you get this situation, this where we have dots just kind of all over and we don't have any pattern, then instead of trying to model and make a curve that fits this, we just say that our data is not correlated. There's no relationship there. Okay? So no relationship seems to exist between these 2 variables, at least not from the data that we've been given. All right? Now, oftentimes when you get this kind of a case, your R-squareds are typically bad. And so you'll see that R-squared being less than 0.6 makes things look like, well, if your R-squared is less than 0.6, then the relationship won't look very good. All right? So my point of saying all this stuff is that just because we have 2 data variables does not mean that we're going to get a nice function. Okay? The 3 that I gave had nice functions, primarily because they were chose to do that. In fact, in the first two cases, I chose specific countries or specific states so that we'd have a nice pattern. If you looked at, all the countries in the world and the number of McDonald's and the happiness level, you wouldn't get a nice pattern that's a quadratic. But in this case, we did because I sort of cherry picked my data. And that is one thing to look out for. If a researcher or somebody is cherry picking their data to make it look a certain way, be very skeptical of that person, all right, and what they're trying to do. All right, so that's my thing on modeling. Again, if you see a pattern that doesn't look very good at all, say it's not correlated, that there's no relationship that exists.